Welcome to ArcGIS Runtime Utilities. My name is Rich and I'll be joined by Jennifer and Tony today. So the utility network is a cross-platform Esri technology for modeling utility and telecom networks. The way it typically works is you create a client-server database using ArcGIS Pro. You set up your schema there, and then you publish utility network and feature services to ArcGIS Enterprise. At that point, you can query and edit data on multiple platforms, including ArcGIS Pro, Web, and of course, Runtime. So today we're going to go through a bunch of different topics. We're going to talk about some of the core concepts behind the utility network, and then we're going to talk about online capabilities. And by online, I don't mean ArcGIS Online. I mean utility networks that work when you are online with a connection to ArcGIS Enterprise. Then we'll talk about offline capabilities using a utility network with a mobile geodatabase. And finally, we'll talk about the road ahead, which is new capabilities that will be available later this year and beyond. So the utility network is pretty new to runtime, and there's still a lot of work to be done there, so we feel it's important for everyone to understand not only where the product is today, but where it's going in the future. Now I'm going to cover a little bit of utility network concepts and things like that, but it would certainly be interesting for you to go back and watch some of the more in-depth presentations on the network itself, including the concepts and lots of the individual details. So if you're looking at this through the PowerPoint slide, there's a link there to last year's talk on the introduction to the utility network. Now I'm going to start by talking about two foundational classes. The first of which is called utility network. How's that for an imaginative name? So this is the central hub of the utility network API. And you can get the utility network object from a feature service URL in a map or from a map directly, and eventually you'll be able to get it from a mobile geodatabase. Now it's worth pointing out that when I'm talking about class names and method names in today's presentation, I am using the names from the .NET API. All of these concepts are transferable to the other APIs, to Qt, to Android, to iOS, and so forth. Then some of the names might vary based on the platform. So the second main class I want to talk about is the utility element class. So the utility element class represents a row inside a utility network, and it may also be a terminal or a percent along of an edge. So this is used in many different places in the API. You can use it to retrieve associations. So you can say, tell me everything that's attached to this particular feature and this particular terminal. You can also, when you get back associations, the features on either side of the association are specified via elements. Elements also specify starting points and barriers for use with tracing. And when you get back individual features from a trace, you get them back in the form of a list of utility elements. So if you need to create an element as an input, there are a set of factory methods called createElement on the utility network class. Now I want to talk a little bit about schema. So one of the good things about the utility network schema is it is very customizable, and in fact every utility network can have its own schema within it. There's no fixed data model. Of course, the downside to that is you need a way of figuring out what the data model actually is. So we have a family of classes that provide this information. So the topmost class is called the utility network definition. There's a definition property on the utility network that returns this thing, and this is how you get to basically everything else in this section. So utility networks are made up of one or more domain networks. We also include a domain network for shared structures such as poles and underwater ducts. So some examples of domain networks would be electric distribution or water or telecom. And we have a utility domain network class that provides information about a specific utility network. Now, asset information itself, this is the actual equipment that you have out in the field, whether it's pipes and valves or lines and devices. Asset information is stored in a fixed set of network sources, and those can represent different things. So for example, electric distribution device and water line would be different network sources. Now these correspond to feature tables in the database, and when I say fixed, there is a specific set of network sources for each domain network. Now that sounds a little restrictive, but the way we work around that is that network sources are broken down into different asset groups for the different kinds of equipment. So for example, transformers, switches, and fuses are all different asset groups within one network source. Plastic pipe would be another good example of an asset group. So in the geodatabase, these are implemented as subtypes. Asset groups themselves can be further subdivided into different asset types. So for example, a single-phase overhead transformer would be one example of an asset type from electric. 4-inch plastic pipe would be a good example of one from a gas or water network. Now, the way that a network delivers a resource is often modeled with a different hierarchy. So this could be a pressure or voltage level. So you may have, to give an electric example, you could have a low voltage network, a medium voltage network, and a high voltage network. In Europe, there's probably there are many more different levels of voltages, and you'll have a different tier for each voltage level. You can also use it to represent parts of the network that can be isolated from one another. So you could have an isolation zone or a cathodic protection zone in a pipeline-based network. So tier groups provide an extra level of organization. Typically, these are used with pipe networks, so you can divide a network into different tier groups, like, for example, transmission and distribution, and each of the tier groups would contain a set of tiers specific to that group. Now, network attributes are fields that are copied into the network topology. You could think of the topology as an index that is used by tracing analytics. So it's much faster for tracing to get the value from the index itself rather than go out to the tables. So typically, attributes that are used in tracing are copied in as network attributes. So some examples would be phase designation for an electric network, or valve position, or pipe material for a pipe-based network. And finally, we have terminal configurations and terminals. So complex junctions can be modeled with multiple logical connection points. So for example, let's take a transformer. So a transformer in an electric network has a high voltage side and a low voltage side. And you could model that as a device with two terminals, a high side and a low side. Or in the case of transformers, you could actually model it using one terminal for each physical bushing on the transformer can where you can attach a wire. So you could have 5 different terminals if you wanted to get to that level of detail. So another example from a water network would be a check valve, and that's a valve where water can only flow one direction through the valve. So you'd have, 2 terminals, and you could specify that you can allow flow between terminal 1 and terminal 2, but not between terminal 2 and terminal 1. So by themselves, these classes aren't that interesting. What I mean by that is you could write a runtime app that displays on the screen the schema of a utility network, but more likely you're something going to be using these classes to build additional functionality on top of. And one of the concepts that is built on top of the schema is a concept of an association. So the associations are connections between features that are stored in the network topology. So we have 3 types: connectivity associations. Connectivity association allows 2 features to be connected without having coincident geometry between the 2 features. So here's one example from an electric network. Many utilities do not want to incur the cost of modeling low voltage cables between a transformer that sits on a pole and the actual house. So what they'll do is they will just simply connect the low side terminal on the transformer to a service point, which is located typically on the side of a house. And you can then connect these 2 features without drawing the line between it and without filling in the attributes for that connection. So what this is typically what this allows you to do is it allows you to do a trace, through an electric network and return the customers as part of that trace without needing to draw the lines between them. The second kind of connection of association we have is called a structural attachment association. Now, this is used to model a physical attachment between a piece of equipment, such as a transformer, and a structure, such as a pole. So what this will do is it'll allow you to do a trace and say, okay, I want to return all the poles that are holding up this particular circuit. And it can do that without needing to go out to tables or traverse relationship classes or anything like that. And finally, we have containment associations. So containment associations allow you to model content stored inside a container. So for example, you have a transformer bank. And by the way, that transformer bank has a structural attachment association to a concrete pad. But inside that transformer bank are fuses, transformers, and arresters. And interestingly enough, there are probably connectivity associations connecting the features within the container, which is attached to the structure. So lots of different possibilities to provide really fine-grained data models. Now, what can you do with associations? Well, there's two particular kinds of queries that Runtime supports. The first is getting associations from a particular element. So an example here, what features are inside this container? So we have a routine for that. We also have a routine to get the associations from an envelope. So this is, show me the connectivity and structural attachment associations within a map extent. So PowerPoint is fun and all, but I think we want to see some code. We want to see some software. So Jennifer is going to walk through how some of the associations work in the Runtime API.
Thanks, Rich. And hello, everyone. I am Jennifer Neri, API developer for ArcGIS Runtime SDK for .NET. In this demo, we will see how associations may be useful in reducing map clutter while providing your apps the ability to inspect relationships within a container. For example, this transformer bank contains transformer, fuses, and connection points. This red dotted line symbolizes connectivity. As we toggle in and out of a container view, we better understand the relationships between features that are not geometrically coincident without displaying all of them at once. Like this switch gear, containing switch, busbar, connection points, and fuses. This blue dotted line symbolizes attachment. And here's how we've done it. Although there were more layers from the feature server endpoint, when we created this WebMap, we did not add all of them. Notice also that some asset groups or subtypes were marked visible false. If your WebMap was authored in ArcGIS Pro 2.6 and up, ArcGIS Runtime will recognize Utility Network as part of your map utility networks collection. Or you can continue to create utility network from the feature server endpoint and add to the map utility networks collection just before loading the utility network. To enter a container view, we capture the map view's current viewpoint before making all of the operational layers visible false. We are using the map view's graphics overlay to display the content features and their associations. We use the GeoView tapped event of the map view to identify an ArcGIS feature from our map. From this feature, we created a utility element and called getAssociationsAsync, specifying this element and the containment type of association. An association is essentially two parts, a from and a to element. Elements not matching the container element's object ID are the contents. We converted these content elements back to features using getFeatures for elements async. A feature having a symbol and geometry may be displayed as graphics. We called getAssociationsAsync again, this time with a combined extent of the content features. and the result of these get associations will have a geometry part, representing the attachment or connectivity. Assigning them distinct symbol, we can display them as graphics as well. To exit the container view, we cleared the graphics in the graphics overlay and turned on the visibility of all the operational layers before resetting the map view's current viewpoint. Take it away, Rich.
Okay, next we're going to talk about another core concept, tracing. So we have a full set of classes to support network analysis. So the technical definition is that tracing entails assembling a subset of utility network elements that meet a specified criteria. So what does that mean in terms of business value? Well, what it does is it helps you answer questions and solve problems about the current state of the network, helps you to design facilities for the future, and really helps organize your business. So Runtime currently provides a subset of utility network tracing functionality, and I use the word subset, but it's not going to be long before I won't need to use that name anymore. The stuff in orange are the new pieces of functionality that we've added just in the past year. So let's start by going through some of the trace types. Connected trace, honestly, it's the most basic trace. Just returns connected features. It's more than anything. It's often for debugging of network problems. Subnetwork traces, on the other hand, are much more interesting. These are collections of connected features. So they tend to represent circuits in electric, and they represent zones such as a pressure zone or a cathodic protection zone in some of your pipe-based networks. So these are typically defined by, you specify that they start at a source or end at a sink. So an example of a source would be a circuit breaker in a medium voltage electric network and a sewage treatment plant for a wastewater network. That would be the sink. And what you typically do is you create this complex thing called a trace configuration that defines the extent of the circuit. So for example, you may define a gas zone to stop at a closed valve. So let's talk about the different subnetwork-based traces. And I'm going to show this little map here. This is an electric network. The blue lines are the wires. The solid lines are above ground cables, and the dotted lines are underground cables. And I'm showing here the circuit source in the lower left. That's your substation, and then your starting point is kind of up there in the center top. So the first kind of subnetwork trace is called a subnetwork trace. It returns the extent of the entire circuit. So in this case, it's going to return all of those blue lines there and all the devices. Typically, this is used to visualize the coverage of a circuit or to perhaps plan inspection and damage assessment work. Now, an upstream trace returns paths leading to the source. So this would typically be used to visualize that path of how power is getting to where you are, and perhaps to find broken devices that are preventing flow to a particular point. I'll contrast that with a downstream trace. A downstream trace returns paths leading away from the source. And typically this is used for things like visualizing the impact of a device failure. The next kind of trace type is an isolation trace. This is used to return devices that must be operated to shut off resource flow to a particular starting point. So your classic example here is your gas valve isolation trace, where you want to, from a given point, say there's a fire or there's a leak or something at a particular point, you want to return a list of all of the valves that must be closed to stop the flow of gas to your starting point. Now, along with that, you can also return the set of features that are isolated if those devices are operated. So going back to the gas trace example, not only do you want to return a list of the valves that you need to shut, but you also want a return of all the customers that will be impacted by closing those valves. The shortest path trace returns the shortest path between two starting points. So shortest can be defined in a bunch of different ways. You can define it as literally the shortest distance with a yardstick measuring out your distance, or it could be a cost. And what I mean by cost is that, say you're routing underground cables between two locations. The shortest path, distance-wise, might be to get out a backhoe and dig a trench through an existing right-of-way. But even though it is a farther distance, it might cost less to route cables through existing ductwork. So you can define a cost that is perhaps, price per meter, and you can use that to find the shortest path. In this case, the cheapest path between 2 points. And finally, we have the loop case, the loops trace. The loops trace identifies features that participate in loops. So loops are often perfectly normal and fine in the case of a water and a gas network, but in an electric radial network, a loop might indicate a problem, and this trace can help you find those problems. So the trace configuration itself is made up of lots of different parts. You can specify starting points and barriers and filter barriers. You can specify the rules for traversability, and that's things like, I want the trace to stop when you find an open switch. You can specify functions to calculate values as you do a trace. What are the number of, how many meters of conductor are in this circuit? You can also specify filters, and filters allow you to return, to specify devices that you want to use to return as part of the results. And these are a little bit different than traversability. So a filter would be something like a valve in a gas isolation trace, or something like a switch in an upstream protective device trace. Output filters allow you to restrict which features are returned as part of the output. And propagators are kind of an advanced way to specify how phase is propagated through an electric network. Now, all of this is to say that this is too much for one Dev Summit talk. It would be half of us talk just to talk about this. I would direct you to look at the Pro SDK talk from last year. It's the Pro SDK, not Runtime, but the concepts are identical and the classes are named very similarly. If you understand how the Pro lets you specify all these parameters, you'll be able to figure out the runtime just easily enough. So you can look for that on YouTube, or you can, if you have the PowerPoint, just click on that link. Speaking of PowerPoint, again, we've had too much of it, and I'm going to hand things over to Jennifer. She's going to walk through a valve isolation trace. You get to see the app as well as the code behind it.
Thanks again, Rich. In this demo, we will see how to isolate a leak on a gas network, determine valves to close, and use squeeze-offs to limit the number of impacted customers. Let's say a gas leak was reported at this location. An isolation trace from this location stops traversability where an isolating tag or category exists. Would include isolated features enabled, the outage area is revealed. Placing a filter barrier at this squeeze-off location would reduce the number of impacted communities. Would include isolated features disabled, the problem valve is now exposed. And here's how we've done it. We created utility trace parameters with isolation trace type specifying a starting location element. Isolation being a subnetwork trace requires providing a trace configuration from a tier in a domain network. We can enable include isolated features to reveal the isolated area. We can provide either a barrier condition in our trace filter or add elements as filter barriers in trace parameters. Calling trace async with these parameters will return us a collection of trace results, which by default includes element trace results. Elements matching the feature table of the layer can be converted to features using getFeatures for elements async and then selected on that layer. Now we have done several improvements since last Dev Summit, and we continue to invite you to explore Utility Network in ArcGIS Runtime. We added support for new trace results. You can add a geometry result type and expect augmented geometries returned. You can add function outputs as a result type and expect a function output for every input function. We added support for new trace types. You've seen isolation trace earlier. You can also do shortest path or loops. You can also compute nearest neighbor with your trace and limit the trace results, returning specific output asset types or conditions. Back to you, Rich.
All right. Now that we've talked about the concepts, let's talk about what functionality is available with online versus offline. So the short answer for online is everything you've seen so far. All the scheme information, all the associations, all the tracing, it's all there. That's great. But there's actually more to it than that. We also have WebMap integration and branch versioning support. So let's go into some details about that. So with web maps, if you publish a web map using ArcGIS Pro 2.7, that's the latest shipping release, with ArcGIS Enterprise 10.8.1, the latest shipping release, and you have a utility network layer in your map when you publish, the resulting map will have a utility network stored in it. So what that means is that there's a new property at runtime 100.10, and that's called utility networks. It's on the map object, and it returns a list of all the utility networks in the map. Now, why is this important? In the past, you had to create a utility network using a feature service URL. That method is still there, but if you don't want to hard code a URL in your application, you can now just get it from the map. So you can imagine an app where you go to the portal, you have the user pick a web map, you open that web map, and then you can get the utility networks directly from that web map. Another thing we support are subtype group layers. So subtype group layers can be published again from Pro and consumed by runtime. So they're called subtype group layers in Pro, and in Enterprise, the runtime class is called subtype feature layer, and we call it that because it inherits from the feature layer class, but they're the same thing. To work correctly with the utility network, you should have one layer for each network source. So typically what you do is you create one subtype group layer for each network source with the sublayers, one for each asset group. And what that does is it allows you to change the symbology, zoom levels, and even the visible fields for each of those asset groups. So you can have a different symbol for transformers versus switches versus fuses, and even show different fields for each of those. It actually looks like there's different tables there when in fact there isn't. So why do we have this one layer restriction? It's worth pointing this out. Association queries and trace results are all returned from the service as a network source global ID pair. So when we have one layer for each network source, so you have a electric device subtype feature layer, you therefore have one service feature table, and we can then build a mapping internally between network sources and service feature tables. This lets us return to you elements that represent features rather than network sources that can't be connected to anything. So technically, you don't need one layer for each network source. If you don't want to display your structures, for example, you can leave that layer out. The key is that you don't want to have more than one. So versioning, let's talk about versioning a little bit. Versioning allows multiple editors to alter the same data without interfering with one another and without creating locks on the database. So feature services supports a thing called branch versioning. The basic idea is that you have a base version called default, and then you have other versions that are created as children to default. So you may have it set up so that each user has their own version off of default. Now, there's a lot of concepts to talk about with versioning. We're not going to go into details here. There are other Dev Summit presentations that go into much more detail on the different concepts behind the versioning. One thing, though, worth pointing out is that branch versioning is not specific to utility networks. So if you're not a utility and you still want to use branch versioning, that's totally fine. So how we implemented this at 100.9, we introduced a class called the Service Geodatabase. and you can get the service geodatabase from a utility network or from a service feature table. And the idea behind it is the Service Geodatabases groups together all of the feature tables, all the service feature tables that are part of the Service Geodatabase. Get versions async allows you to get a list of all of the available versions that your user can get to. And if you don't find the one you're looking for, you can use create version async to create a new one. Most importantly, switch version async switches the version for all of the tables on that Service Geodatabase. This helps ensure that all utility network feature tables point to the same version. So some versioning functionality that we don't support in runtime. We don't support the ability to delete a version, and we don't support the ability to reconcile and post. And quite frankly, we don't see these as common mobile workflows. We see these as things that take place back in the office. So to demonstrate how this works, I'm going to turn things over to Tony, and he's going to do a trace against default and against the version, and then show the code for both the trace and for switching the version.
Thank you, Rich. My name is Tony Joaquim. I am a senior product engineer on the ArcGIS Runtime SDK team for .NET. In this demo, we will do a utility network trace and check associations on the default version. Then we will switch to a child version that has edits on it and do the same operations again. We will examine how the trace results and associations differ between the two versions. After loading our data from a WebMap, we can obtain the utility network instance from the map.utilitynetworks property, if the map has any data that is part of the utility network. From the utility network instance, we can get access to the Service Geodatabase. The Service Geodatabase gives us access to the version name property, that is the version we are currently connected to. If we examine that, we will notice that we are currently connected to SDE.default version. The Service Geodatabase also gives us access to the getVersions_async method that returns a list of all the versions on the service. In this case, we use this method to populate this combo box. We will start our trace by adding a starting point and a barrier. Then we will call trace async, and then we will examine the results returned. Now, if we enable get associations on the viewpoint changed event, if we pan, we will notice associations in the middle between the features. One feature in particular of interest is the following feature over here. This is a fuse. This feature is deleted from the child version. In this SDE default version, we notice how this feature has associations on it. Now we're going to switch to the child version. We're going to pick the version we're interested in and call switch version async on the Service Geodatabase to switch to the child version. After calling a reset, we're going to do the same operations we did on the SDE default version. First, we notice that the feature we're interested in no longer exists in the child version. We're going to start our trace by adding a starting point, then adding a barrier in the similar locations that we did before, and then call trace async on it. Notice how the trace results differ from the trace results we had on the default version. This is mainly because of the deleted feature and the deleted connectivity on it. Now, if we pan, we will notice that the associations also have been removed from the child version. This demonstrates the ability to switch between versions and supporting that with the utility network operations. Here's how we implemented this. We start by creating a new map referencing a web map containing the utility network layers we are interested in. Then we await load async on the map. We verify that the map contains at least one utility network. We get a reference to that utility network and await load async on it. On the Service Geodatabase, we call getVersions_async and populate the results in a combo box. To define the starting points and barriers we use in the trace, we start by creating a utility trace parameters variable. Then in the onGeoView tabbed event, we do an identify. From the identify layer results returned, we get the first or default feature. Then we call utility network.create element, passing in that feature. After that, we add this element to the starting locations or barriers in the utility trace parameters based on the user's choice. When we click on the trace button, we start by clearing selections on all operational layers. Then we call trace async on the utility network, passing in the utility trace parameters we defined earlier. From the trace results, we get the first utility element trace result. Then for each operational layer, that is of type feature layer, we get the trace result elements for that feature layer. Using the getFeatureForElements async method, we get the features. Then we select these features in the layer. For the associations, we have a method that we call from onViewPointChangedEvent. In that method, we get the map view extent using mapView.getCurrentViewPoint. Then we call the utility network.getAssociations async, passing in that extent. For each of the associations returned, we define a symbol. Then we add a graphic to our graphics overlay using the associations geometry and the symbol. For switching versions, we make use of the utility network.Service Geodatabase class. This class has a switch version async method defined on it. We pass in the version name from the combo box selection. This allows us to switch to the version we want. Any UN operations after that will be happening on the data in that version. Thanks. Back to you, Rich.
All right, thank you. So Service Geodatabases also fully support editing. There's a pair of routines called apply edits async and undo local edits. What those do is they save or revert all of the edits that have been made to the version using the same database transaction. So in the past, you had to go through each service feature table and apply the edits to each one individually. Now you can do it all in one transaction. The Service Geodatabase also supports multiple session types. Now, for most cases, transient is going to be the one you use for a typical mobile application. But you can also create what's called a persistent session type. And persistent session type will, if you're using a version other than default, lock that version to other users to provide better data consistency. So this is really more applicable for creating a desktop application and not really for a mobile thing. Again, just to remind people that the Service Geodatabase isn't specific to utility networks. You can work with any branch versioned feature service. So that was the online story. Now let's talk about using utility networks while offline. So first of all, utility network feature classes can be taken offline. You can use sync from runtime. This is what the two runtime classes are: offline map sync task, which takes a WebMap and creates an offline map for it with a mobile geodatabase, or the geodatabase sync task, which takes a feature service and basically converts that into a mobile geodatabase. And the other possibility for read-only data is you can use ArcGIS Pro and create what's called the mobile map package. Now, subtype group layers work fine with offline maps. That's good. And you can edit utility network features if you're using sync. Now, the important difference here is that when you're editing online, or when you're editing with Pro, dirty areas get created when you edit features. The dirty areas tell the system that the data in the database tables is different than the data that is stored in the network topology. So then as a separate step, you call validate network topology and get those back in sync. So when you're editing offline with runtime, those dirty areas are not created at the time you edit. They're created when the data is synced back to the service. And likewise, if you have any attribute rules set up against that service, those rules will run when you're syncing the data back. Now, there's no support for utility network functionality yet offline, so there's no access to schema information associations for tracing. So that's unfortunate, but it leads us into the next slide where we start talking about our plans, the rest of the roadmap for the utility network. So I kind of divided this up into three main areas, short-term stuff, medium-term, and long-term. And they're more or less in the order that we expect to do them in. As you can guess, I'm not going to give dates, but we can talk more about that during the live Q&A. In terms of taking utility networks offline, the offline map sync task and the geodatabase sync task are both being enhanced to take core utility network information offline. So for phase one of this, what we'll get is schema information, all the associations, so you can visualize your data in the field, including containers and all the structural attachment and containment associations. Map integration is fully there. What that means is you'll be able to ask an offline map for its utility network, just like you can ask a web map. Subtype group layers, I think I've already mentioned, are there. That's great. Branch versioning, not really applicable. Once your data is in a mobile geodatabase on your device, there's no more versions. And tracing is not yet supported. Now, in terms of editing, it's really the same capabilities as before. So the other thing we're working on in the short term is a thing called a named trace configuration. Now, this will start off working online. And what it is a named trace configuration basically allows the data model specific parameters of a trace to be kind of treated as a black box. How it works is you create this in ArcGIS Pro, you create named trace configurations, typically a domain expert, somebody who understands the intricacies of the data model and understands where all the network attributes are and all that. They create it in Pro and then publish it to the utility network service. In addition to that, when you publish a web map from Pro, you can include which named trace configurations you want associated with that web map. So if you're creating a web map for electric users out in the field, you would take a handful of electric traces and add that to that map. So what this does on the runtime side is it allows runtime developers to write this tracing code without needing to understand what the data model is. They get the trace from the web map. They see it's called Upstream Protective Device Trace, to give one example. The name trace configuration tells you how many starting points you need. The app developer gets those by asking the user to click on the map or what have you. They run the trace, they get the results. You know what type the results are in, you display them on your screen. You don't need to know the individual fields that are queried as you're doing this trace. This also allows you to write an application that runs with various different data models, right? You can write an app that does an upstream protective device trace without knowing what the data model is. That same app can work with 3 different companies' data models. In fact, I go so far as to say this could even be domain independent, right? You don't even need to know that an upstream protective device trace works with electric. All you need to know is you have a map, you have a set of traces that work with it, user picks a trace, runs it, displays results. You don't need to know anything beyond that. Something we're working on in kind of more of a midterm time frame are support for display filters. What display filters do is they turn off the display of features based on a filter. Now, runtime already has a thing called a definition query, but the definition query actually restricts the feature from being returned by other queries, whereas this display filter just turns it off when you're drawing it. So this is not a utility network specific thing, but it is often used by the utility network. And what most people use it for is to hide features that are stored within containers. So what that means is that you'll see on your map, you'll see one feature which represents a switch cabinet, and then you'll provide to the users a tool that you click on that switch cabinet with like a container tool, and then you see the contents of that container. But on the main map, you don't have your map cluttered with the 20 features that are inside that switch cabinet. So this is currently working in Pro. It's migrating to the WebMap and then to runtime after that. We do want to add support for limited offline editing. And what I mean by that is we want to first address the problem of association editing. And the workflows we're looking at there are for things like field data corrections. So you look at your device and you see there's a transformer attached to a pole, and then you look up from your device out at the real world and you say, whoops, that transformer's at a different pole. You'll be able to use the software to delete that structural attachment association and then add a new one to the correct pole. Of course, this is going to respect all the rules that are configured with your utility network. So if you have a rule that, for example, suggests you can't put a power pole inside a switch cabinet, which is a good rule because you couldn't do that in the real world, the runtime will respect those rules as well. And the other thing here is respecting association deletion semantics. Right now on the service, you can set the configuration up so that when you delete a structure or a container, such as a transformer bank, you can either prevent that deletion unless the contents have been removed, or you can automatically remove the contents, or you can delete the contents when you delete the container. So all of that would be respected in runtime. Obviously, the big piece of functionality that everybody is waiting for is offline tracing. This is a major cross-team development effort for 2021. We currently have 3 different teams working on it: the utility network team for the core tracing, the feature sync team to move the topology tables out into the field, and of course the runtime team as well. So I can't give you a date on this yet, but this is an area of intense focus within Esri. Finally, we want to add additional editing capabilities over time. We want to support attribute rules, both the batch rules. You want to be able to execute those when you're online on the service, and when you're offline, we want to be able to handle the immediate rules that take place when you're editing features. Contingent validity is another good one. It's, again, not specific to utility networks, but many utility networks take advantage of this. The classic example I give is, so what it is, I guess I should say that first. What it is that the value of one field can control the value of other fields on the same feature. And the classic utility example is that you have a pole, and the pole material, when the pole material is wood, the allowable values for the pole treatment type attribute are paint, none, or creosote. That's how you treat the pole, so it doesn't rot. Now, when the pole material is set to steel, the allowable values for the treatment type become none and painted, because you can't put creosote on a metal pole. That's the sort of thing that contingent validity supports. And finally, of course, we want to support validate topology. We'll do it online first, and then eventually we'll take that offline as well. That is the end goal for this project. So before I open it up for questions, just want to go over some additional sources of information. Some additional Dev Summit sessions you might be interested in. There's one called Network Management with ArcGIS, deep dive into the capabilities of the utility network. Another one is Version Management with ArcGIS, if you want to learn more about versioning and how it works under the covers. And then finally, of course, if you're new to runtime itself, maybe you're an experienced utility developer, but haven't done a lot with runtime, there are lots of sessions called Building Apps that work against all the different platforms supported by the runtime. I have put a link in here to last year's session. Last year's session contained a lot of additional information about annotation and about taking data offline. We kind of ran out of room this year to put all that in, but you can go look at last year's, and that information is available. We have a link to the sample code that you saw during these demos, so you can go and try it out for yourself. And then finally, a link to the ArcGIS Runtime developer site. Thank you very much for your patience, and I'll now turn it over to the live Q&A. Hi, everybody. So the presentation you just saw was actually pre-recorded about 6 weeks ago, and we were in the middle of the product development. So I wanted to give a little bit of an update of things that have taken place since that time. First of all, I did make a statement that said that utility network features can be edited today as simple features. That actually is not true. We found a bug in this in runtime 100.10, and that bug is fixed in 100.11. So this statement will be true then at 100.11. That, by the way, is planning on shipping later this month. The other thing is I didn't give a date on taking utility networks offline because, like I said, we are still in development. At this point, I can say that this is definitely in 100.10. So being able to take it offline with schemas, associations, map integrations, and so forth. I did get a question on the Q&A about why is branch versioning not applicable? And the reason that is just that once you take it offline, there's no branches in the mobile geodatabase, you're just editing. When you sync your changes back to the service, it will sync to a particular version that's there. And name trace configurations, I'm glad to say, also made it into the product. So that is there. It does require ArcGIS Enterprise 10.9, which is shipping in May. But if you're building an app and have access to the beta, you can start hitting that now. So with that, that's all for the addendum. We can turn it over to live questions. So have a couple here. We got a question from Jason. If the affected area is beyond the scope of the current map extent, does the trace change the extents and retrieve all the data? How about you take that? I forget who was going to answer that one.
I can. Basically, thank you, Rich. So basically, when we do a trace, online trace, the results from the trace are returned to the client, to runtime in this case. And we have the choice to take these results and display them on the map. We currently do not have the ability to do any offline traces. So once we get the results, we can display, select the elements returned and display them as graphics if you want. Back to you, Rich.
Maybe I can add to that, to what Tony had said. So when you get the trace results, you'll be able to select them on your feature layer and be able to get an extent for those results and be able to change, you can call set viewpoint, and be able to change the extent that you're in. Next question. Rich, I think you're on mute.
It's only been a year of Zoom meetings. How can I not know how to unmute myself? And I made the same joke yesterday in my other session. So Runtime app makes direct changes to the feature service. You can add and update features. What will happen is that when you make those edits, when you call apply edits, it will on the server go ahead and create those dirty areas for you. So it all takes place automatically. The nice thing of having server as the back end is server doesn't let you create bad data, right? It will correct it and make all the changes it needs to. It also runs any attribute rules that you've set up on the server. Question, can runtime currently do validation online? There's nothing in the runtime API right now to do that. If you are online, you can always make the REST call yourself automatically, but that's something that we'll be adding.
If I may add something,
Sure.
The utility trace configuration also has a validate consistency parameter, which you can set to true, and this will validate the results if you're hitting dirty areas.
Do you want to answer the question about definition expressions?
Sure. So we have a question here. Will I be able to apply a definition expression on my layers and still be able to do associations or trace? This is actually a good follow-up. We had a GeoNet user who posted a question some time ago that they have subtype feature layers, and they don't want all of the features visible. And this is where they have to turn off some devices and asset types. I'm happy to say that this will be supported in our upcoming release 100.11. So there will be a property for the utility element that you get, and the isValid property will indicate whether it's something that you can transform into features, which means a feature that exists on your layer, but the global IDs there and all other information will be accurate. So you will get the trace results. It just won't be a feature that is already on your map.
Did it again. How can I edit different versions with runtime? I think we answered that in the demo.
Did you want me to go over it again? I can do that. So basically with the utility network, we have a property that's exposed on it that's called the Service Geodatabase. The Service Geodatabase class has a method in it to get the list of versions that we're interested in and that exist on the server. And in addition, there is a switch version async method that we use in order to switch to other versions. So by default, we're usually on ste.default version. And then you have the option to switch to a different version in order to see what somebody else has edited on it for a workflow, or if you want to do any edits on the specific version. So that's how we get to a different version and edit that. Back to you, Rich.
Yep. I think we are out of questions. I will wait a few more minutes in case someone is typing as fast as they can. Let us know too if the answer we gave doesn't make sense, and we'll pick it up. One thing that I could mention that we didn't talk about, when you do take a utility network offline, someone was asking about versions. It is configurable on the server of whether you create one version per user or not. That's typically how it's done. I think you can also do it one per map. Is that right?
It's usually, so when you publish, if you enable basically replica tracking on your data, then you have the option to either create a version per replica or a create version per user. And that basically is what dictates if a version gets created for one user, if he has multiple replicas, or if multiple versions are created, one per replica. So every time the user calls, for example, generate geodatabase, there's a new version that gets created, and that version will be there so that if the user did a sync back to the server, that's where the edits will go to.
We got one more question. Can you create versions while offline if there's an unexpected change someone needs to make? And the answer to that is no. When you're offline, you don't have a connection back to the service.
Right.
But the version is created when you take your data offline. The version can stay there on the server. If you don't make any edits, it's fine. If you do make any edits, when you come back and do the sync, it will push those changes up into your database. All right. Well, thank you all very much for attending. I hope you're enjoying this this virtual conference as well as you can. Looking forward to seeing everyone in Palm Springs in March of 2022. Let's keep our fingers crossed. All right. Thanks, everyone. Bye.